So the next rule we need to deal with for taking derivatives, and fortunately the last rule that we need to take care of, is the chain rule, which is used for functions inside of functions. Let me write that down for you. Functions in functions. So you may have come across this type of function or this type of structure in advanced functions where you did composite functions. So you did the sine of a parabola or a logarithm squared or something like that. So I'm just going to give you an example of a function that looks like this. So f of x is, let's say, the sine of 3x to the 4 plus 2x plus 7. Okay. So what you need to be able to see here is that this is not sine multiplied by this power 4 here. It's the sine of this. And that's a critical distinction. If it were a sine x multiplied by this parabola, you'd use, or power 4, you would use product rule. But because this function doesn't actually have its own argument, you have to treat it like a function in a function. So in a second, I'm going to show you how to tell the two apart. But for now, I'm just going to look at this thing here, and I'm going to get out my my pink marker here. And the first thing I'm going to do is I'm going to notice that I can put a circle entirely around that. So that's my innermost layer of this function. Then I'm going to get out the blue marker, and I'm going to draw a circle around that. You notice that this pink circle is entirely contained within the blue. So that's how you see a function in a function. This thing is entirely contained within the sign. So the way the chain rule works, and I'm just going to do it, and then we're going to talk about why it works later, is to take this derivative. You need to determine the change in the outer layer first, and then you multiply it by the change of the inner layer. Okay, so I'm going to look at this outer layer, and I'm going to forget everything that's in the pink. I see a sine. The derivative of a sine is a cosine. And the derivative of that sine is the cosine of whatever was inside of it. So I'm just going to take this, I'm going to copy and paste it into that bracket. So similar to product rule, when you're doing this, you take the derivative of the outside piece, leave the inside alone. Now we're going to take the derivative of the inside piece. So this thing here, the derivative of this layer, you notice that there is no sign inside this layer. There is only the power 4. So this box should only contain the derivative of what I have circled in pink. So here, bring the 4 down. 3 times 4 is 12. Keep the x, drop it by 1. 2x to the 1, bring the 1 in front. That's 2. Keep the x, drop it by 1. And the derivative of any constant is gone, so that's just 0 on the back. So to clean this up, it is a good habit to write things that are multiplying cosines in front. That way you know that it is this multiplied by the cos of that, not the cosine of these two things multiplied. That's a subtle difference. But it will help to write it out this way. So I'm going to write this bracket first. It's 12x cubed plus 2. X to the 0 is just gone. Multiplied by the cosine of 3x to the power 4 plus 2x plus 7. So again, just to go through how this works, I've circled my bits from the inside out. I saw that there were two layers, a layer that's a power 4 and a layer that's a sine. I took the derivative of the outer layer, the sine part, and because this is contained inside that blue bubble, it followed along. Once I had that one done, I multiplied by the derivative of the next layer in. Rearranging so that this comes first, just so I can see that it's that multiplied by a cosine, and I'm good to go. So I'm going to do two more examples of this. One that's 2 layers deep, and then one that's 3 layers deep. And then we'll try and see the difference between a chain rule and a product rule function. Okay, so I have a cosine shoved inside of a radical. So the first thing I'm going to do to that is write the radical in fraction exponent form so that it's a little easier to apply the power rule. So this thing is a cosine of x raised to the exponent 1/2. Now, if I do that and I color in my layers, this is what's on the inside. I've got a cosine here, completely contained inside of something to the exponent 1/2. See that happening? It's a bubble in a bubble. So, to do my derivative, because I have a function entirely contained inside of another one, I'm going to need to do the derivative of the outer layer, and then I'm going to need to do the derivative of the inner layer. And I will be multiplying the two together. So, if I work through that, the derivative of this outer layer is bring the exponent down, drop the exponent by 1. And this pink thing is within the blue bubble, so that argument follows along. Now that I've done the derivative of the outer layer, I do the derivative of the inner layer, and the derivative of cosine x is negative sine x. So to clean that up, negative times a positive is a negative. The only coefficient I have is this 1/2. Cos x to the negative 1/2. Well, that's a cos x in the bottom because of the negative, and square root because of the 1/2. This thing here is a sine x. So to bring that all together into a single fraction, I have a negative. The only thing, that's going to jam up on me. The only thing in the numerator is going to be the sine x and this negative here. I'm just going to write the negative up front. I have sine x up top, and I have 2 square root cos x in the denominator. So this is the calculus part, right? Taking this function and finding its derivative. That's the only place we did any calculus at all. Everything after this is just flipping the notations and then cleaning it up so that it's a tidy little package. So again, just like the last example, I took the function, I found the inner layer and the outer layer, and then I just started from the outside and worked my way in, like you're peeling an onion, right? You deal with the outer layer first, and then you deal with the inner layer next. Okay, so I'm going to erase this, and I'm going to try one that is more than 2 layers deep, so you can see what happens there. All right, so first off, I have a 1 over sine. Now, the first thing I'm going to do is to write that as negative exponent notation so that it's more easy for me to apply the power rule. So this is a sine x squared minus 7x plus 2 all in the denominator. So if I get out the markers to circle this, right there in the center I can see this parabola here, And then that parabola is shoved inside of a sine function, which I have here. And then that sine function is shoved into a rational expression. So you notice that there's a loop in a loop in a loop, right? Each of these functions is embedded in some other one. So this chain rule is going to have a pink layer, a blue layer, and a yellow layer. It's got 3 parts to it. So I'm going to write that out. dh by dx equals the derivative of the outermost layer, the derivative of the middle layer, and the derivative of the inner layer. Okay, so when I go through this, I'm going to have to be careful to only keep the things that are contained within each layer. So here we go. Find the yellow loop. That's here. The function in the yellow loop is the exponent -1. So exponent -1 comes down in front, and I drop the exponent by 1. Then I look to see what's contained within that. I need to keep my argument without modifying it. So I need to put that sine of x squared minus 7x plus 2 into this bracket. Oops, minus. Good. The yellow layer is done. Now that that's done, I go in to find my blue layer. That's here. That's a sine. The derivative of a sine is a cosine. And I just need to keep whatever argument is within that blue loop. My x squared minus 7x plus 2. And then for my pink layer, I look in there. The only thing within the pink is the parabola. So I need to do the derivative of the parabola, which would be 2x minus 7. Don't need quite so much space for that one. And I'm done. That's the calculus part. So if I look at what I can clean up here, I have this in a numerator, I have this in a numerator, and I have this in a denominator. So my derivative then would be negative. This is up top, and this is up top. And just for grammar, we write these things first. It's not wrong to write them second, but it can be a little confusing. It's nice to see that it's this times the cosine, not the cosine of this times that. And then I have a sine of x squared minus 7x plus 2 squared in the denominator. There you go. Tied it up. Okay, so it didn't matter that it had 3 layers. It just meant that I needed 3 pieces to this derivative. If this had 4 layers, there'd be 4. If this was 5 layers, there'd be 5 little boxes. And you just start on the outside and chisel your way in until you finally have done the last derivative in the chain. Okay, so I'm going to erase this, and I'm going to draw a function that requires just chain rule. And then I'm going to draw a function that requires just product rule, and we're going to try and figure out the difference so you can see which rule you should be applying. Okay, so I have k of x being sine x times ln x, and I have mx being the sine of root x. So that's your first clue. When I read this, I had to write it as sine times ln. Okay. Whereas this one, I said sine of root x. So sine x times ln x, or sine of root x. You notice that this has a big fat of in it, and this had times. Well, product, that word, literally means multiplication in math. So the fact that you had times here, that gives it away. this word of implies that the function is in the other one. So if you see that word, that's telling you that it should be chain rule. The second way we can look at this is by drawing those circles. Right? When we did product rule, there was a piece here. So I draw a bubble around that piece. And then I'm going to draw a bubble around the other piece. Like that. Do you notice that those bubbles do not intersect? This is entirely contained within the pink. This is entirely contained within the yellow. And none of this is in the yellow bubble, and none of this is in the pink bubble. They're totally separate. Oh, this is feeling a little juicy this morning. Let's clean that up. Gross. This function, on the other hand, if I draw a circle around the square root, and then I draw a circle around the sign, I wasn't able to draw a circle around the sign without including that pink piece. So when you have them like this, when they are separated, this is a product rule setup. Right? You're going to have to do the derivative of this, leave this alone, plus leave this alone, then the derivative of the second. This one, however, is a function in a function. You can see it with the loops. That's chain rule. So if you try drawing these loops around things, it will help you to distinguish which rule you need for which part, especially when we get into the more complicated parts or more complicated functions where you need to do both product rule and chain rule in order to get your derivatives. I'm going to erase this, and we're going to do an example of chain rule where I try to give you a justification for why it works. Okay, so now that you've been through a few examples of it, you will look at this and you should be able to know that the derivative of this would be the derivative of ln x multiplied by the derivative of sine ln x multiplied by the derivative of the radical. So this line here would be 1/2 bracket sine of ln x n bracket to the negative 1/2 multiplied by cosine of ln x multiplied by 1 over x. So that's it. That's all you need to be able to do in order to answer a chain rule type derivative. What I'm going to do right now is the formal formal write-out of exactly what you're doing here in order to make that possible. So the idea is that when you look at this in the first place, this is too complicated to do. That I have functions in functions in functions, so I'm going to try and simplify it down to basic functions so that I can apply my derivative rules. So the first thing I'm going to do is I'm going to let p replace the ln of x. I'm going to get rid of that. Well, what I'll have then is b no longer as a function of x. I'll have b as a function of p. And you're allowed to do that in math. You can replace something with something else as long as you make notes about what you've done along the side so that you don't miss that information. Well, that worked. I mean, this is more simple than this was. So if I could replace the ln x with a p to make this look easier, then I bet I could replace sine p with something else in order to make it even easier than it already is. So I'm going to let q replace sine p. Why not? What I have then is b as a function of q is the square root of q. Okay, great. Now here's the trouble. I can take the derivative of that. It's just a basic function. But when I do, I will have BB, or dB by dq. And I don't want dB by dq. I want dB by dx. So I'm going to use a little trick about fractions. So just to bring this to your head with numbers before I get too complicated. If you have a fraction, let's say 3/5, you've been doing, like with common denominator, a little trick like this. You double the top and you double the bottom. And that would give you 6/10, and that's equivalent. Well, I'm going to rewrite this a different way. I'm going to put the 3 over the 2 and the 2 over the 5. Now, this is worth the same as that. Because if I were to try and simplify it, I have a 2 in the numerator and a 2 in the denominator, and they divide each other out. So leaving only 3/5. So there's nothing wrong with this, right? I can take this fraction here and I can make it as miserable as I like, right? I could do 3/2 and then a 2/7 and then a 7/11 and then an 11/5. And that's okay because this 2 divides that 2 away. This 7 divides that 7 and this 11 divides that 11, leaving only the 3 and the 5 behind. So there's nothing wrong with that. So I'm going to abuse this little property of fractions to try and build dB dx out of some other pieces. So I'm just going to clean this off the board so you can see how that works. Alright, so the thing I want is the derivative of b by x. Okay. So I'm going to find b. There it is. I don't have b of x. I have b of q. So I'm going to write that in there. I can't give you dB dx, but I could give you dB by dq. Okay. Well, those aren't the same, so I need to keep building. Do I have q in terms of something else? Well, I do here. I could take the derivative of this and get dq, but it wouldn't be dq by dx, it would be dq by dp. So let me jot that in there. Well, that's still not equal to this because I don't have everything canceling out. So could I take a derivative of p? Well, I could. It would be dp by dx. So I'm going to jot that in. dp by dx. And then I'm going to take a look at this chain of fractions that I've met. Hence the chain rule. This dq is going to undo this dq. This dp is going to undo this dp, and that will leave only dB by dx, which is what I'm after. So I'm going to just sort of write that out then. dB by dx is going to be this piece here, dB by dq, and then this piece here, dq by dp, and then this piece here, which is dp by dx. So I just have to go back through my list of garbage and figure out what that is. So find b of q, that's there. So the derivative of this thing would be, that's just a radical, so 1/2 of whatever to the negative 1/2. And the thing that's in there is q. Fine. This box needs to be dq by dp. So I find q and p. The derivative of this by p, and this is just a sine. So the derivative of a sine is a cosine. And it would be cosine of p in that bracket. And in this last bracket, I need dp by dx. So here's p as a function of x. The derivative of this would be 1/x. and I'm done. So I mean, technically that's finished. That is the derivative of b by x, but it's a bit rude to be asked for x's and to hand someone q's and p's. So I'm going to go back and I'm going to find p in terms of x, and I'll find it right here. I'm going to replace my p with ln x. Basically, I'm undoing the replacements I made before. I also am going to replace this q here with my sine of p. But that's not going to fix it, right? I'm going to still have a p in there, so I'm going to have to put my p into there. Ln x for p, and then sine of ln x for q. If I fill all that in, db by dx is 1/2. Q is sine of p. Right? But I don't want p's, I want x's. So I have to find p in terms of x. That's here. So don't write p. Write what p is worth. Ln x. Next bracket, I need the cosine of whatever p is worth, and that's here, cosine of ln x. And the last box, I already have x's. So there you go, I'm done. So I'm going to erase this stuff in the center, and then I'm going to just do some loops on this function originally, so if we can see how this was built based on how that was built. Okay, so looking at this thing, doing it the quick way, I have an inner layer here. I have a middle layer here. And I have an outer layer here. So to do this the fast way, dB by dx would be the derivative of my outer layer of the onion, and then the derivative of my middle layer of the onion, and then the derivative of the last layer of my onion. So working through these three layers, the derivative of a square root is 1/2 to the negative 1/2 of whatever's shoved inside there. So the thing inside the square root is sine of ln x. Okay, good. Next layer in is the blue. The derivative of a sine is a cosine with whatever the argument is just shoved in. Now I'm down to the pink layer. The only thing in the pink layer is this ln. So the derivative of a ln is 1/x. And if I look at the pieces I have here, I have forgotten that. I have 1/2 sine ln to the negative 1/2. That's this bracket. Cos of ln x, that's that bracket, and 1/x, which is this bracket. So the quick way works, and this is how I want you to do it. But if you need a justification, right, or if you're ever asked to prove the chain rule, you need to use that series of replacements and the fact that this derivative, d by dx, is the same as db by dA, dA by dc, dc by df, df by dg, dg by dh, etc., 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 as long as the last one in the chain is dz by dx, or whatever, by dx, so that this cancels this, this cancels this, this cancels this, this cancels this, this cancels what came before, and I'm left with b/x. And all of these things are multiplied. So give the practice problems a try, and then in the next section we'll be doing derivatives where they require product and chain rule.